We're going to start chapter 7 next. So in chapter 7, we're going to be talking about functions. So we're going to examine different types of relationships on sets. In chapter 7, we're going to be looking at functions, and in chapter 8, we're going to be looking at relations. So in terms of sets, ordered pairs can be written as Cartesian products A cross B that is defined as the set of points x, y such that x is in set A and y is in set B. A relation R from A to B is a subset of A cross B, or A times B. Given an ordered pair x, y in A by B, x is related to y by R if and only if the ordered pair xy is also in R. The set A is called the domain of R, and the set B is called the codomain of R. So first point of difference when talking about functions, we have a domain, we have a codomain, and we have a range. So we don't just have a domain and range. We now have a domain, a codomain, and a range. We will get to the range in a moment. A function is a special type of relation. A function, f from x to y, denoted as f colon x right arrow y, is a relation with domain x and codomain y that satisfies the following two properties. Every element in x is related to some element in y, and no element in x is related to more than one element in y. Thus, given any element x in the set x, there's a unique element in set y that is related to x by f. If we call this element small y, then we say that f sends x to y, or f maps x to y. We would write it as f colon x arrow y. The unique element to which f sends x is denoted f of x and is called f of x, or the output of f for the input of x, or the value of f at x, or the image of x under f. Most of us have already seen function notation and would already read it as f of x. So we've talked about a relation, we've talked about a domain, a codomain, and a function. Now this is a very similar definition to function that you've heard before. Every x has only one y. The only thing, and that's basically what we're saying in requirement 2, the only thing that makes this different is that in requirement 1 we're saying that every element in the domain x has to be related to some element in the codomain y. So that's a slightly different way to consider domain from the way you probably learned functions in algebra or pre-calculus. So now that we've talked about domain and codomain, let's see how range relates to domain and codomain. So the set of all values of f taken together is called the range of f, or the image of x under f. So we say the range of f, which is the image of x under f, is the set of y, elements y in the codomain such that y equals f of x for some element x in the domain x. In other words, the range is the set of elements in the codomain that are being mapped to by the function f. So if not all elements of our codomain are being mapped to the codomain and the range are different sets. And we will have a visual representation of this that will make it a lot easier to notice and to understand and to comprehend. So if we are given an element y in the codomain, there may exist elements in the domain X with y as their image. When X is an element such that f of X equals y, then X is called a pre-image of y or an inverse image of y. You've probably heard something very similar to that. And the set of all inverse images of y is called the inverse image of y. So we define the inverse image of y as the set of all elements x in the domain such that f of x equals y. So this is a lot of definitions, and I will say that using these arrow diagrams brings these definitions to life. So let's look at our arrow diagram. If x and y are finite sets, you can define a function f mapping x to y by drawing an arrow diagram. You make a list of the elements in the domain X and a list of the elements in the codomain Y, and then you draw an arrow from each element in X to its corresponding element in the codomain Y that is mapped there through F. So let's do a little bit of exploration with the arrow diagram from the last slide. So here we have a function f that's mapping from domain X to codomain Y. So here is our domain X and our codomain Y. The elements in the domain of F are the elements in the left circle. So that is the answer to part B. What is the domain of F? Well, that would be the set X, which is X1, X2, X3, and X4. That would make the codomain Y, which is the set of elements Y1, Y2, Y3, Y4, and Y5. Does F represent a function? Well, remember the requirements are that every element in the domain must map to an element in the codomain. X1 maps out, X2, X3, and X4. Okay, so we met that requirement. And then the other requirement is that each element of the domain can map to only one element in the codomain. Well, let's check it. X1 only has one arrow going out, X2 only has one, X3, and X4. So it's looking like a function to me. So we would say yes, because every element in the domain X maps to only one element in the codomain Y. So I put both rules kind of into one sentence there, and that's okay. So we have our domain as our set of x values. Our codomain are the possible sets of y's that they could be mapped to by the function f. But remember, the range is the set of y values in the codomain that are actually being mapped to. So if we look at our diagram, y1 is used. Here, we'll highlight them. Y1 is being mapped to, Y3 is being mapped to, and Y4 is being mapped to But y2 and y5 are not being mapped to, so our range here is only y1, y3, and y4. One more time, remember that the range could be smaller than the codomain. The range is a set of y values in the codomain that are being mapped to by the function f from the domain x. If not every element of the codomain is being mapped to by f, then we have a smaller range than we do the codomain. For part E, part F, and part G, these are actually a lot easier than you think. This is just literally taking that idea of function notation you've known and applying it to this problem. If I asked, what is f of x1? Well, here's x1. F maps x1 to y3. So we would say f of x1 is equal to y3. In the same manner, f of x3 says that f maps x3 to y3, so it's y3 again. So f of x3 is also y3. So f of x4 would map to y4. So none of this is particularly new in terms of function notation or things that we know about functions. What might look slightly different are the questions I'm asking in H, I, and J. In H, I said, what is f inverse of y4? The inverse image of y4. Well, this is where we look at y4 and we figure out what set of elements in the domain are mapped to y4. In this case, it's only x4. So the inverse image of y4, and remember, this could have more than one element, so we write it as a set, and in this case, it's only x4. If I ask what is the inverse image of y2, then we have to look at y2. Well, y2 isn't being mapped to by any element of the domain, so the inverse image of y2 is simply the null set. On the flip side of that coin, if we look at y3, its inverse image is that it's being mapped to by two different elements of the domain, both x3 and x1. So the inverse image of y3 is the set x1 and x3. The definition of what a function is and what it requires, those two requirements, are why we don't have to put parts E, F, and G into set notation. Because if this is a function, x1 will literally only map to one value. x3 will map to only one value. x4 will map to only one value. It will never be a set. If it were a set, it would not be a function. So we do not need function notation, we do not need curly braces for set notation when we're doing evaluation of an element in the domain of our function, an f of x, because it can only be mapped to one y in the codomain. But now when we're going from the codomain back to the domain, we don't have that same limitation. So we could have more than one element of the domain mapping to the same element in the codomain, which is what we found for element y3. So we need to use set notation for inverse images. And lastly, I asked for you to represent the function f as a set of ordered pairs. Well, in that case, f would equal a set of ordered pairs where x1 maps to y3. Let's see here, comma, let's see here, x2 maps to y1, comma, x3 maps to y3, comma, and x4 maps to y4. And that is our set of ordered pairs for what f, our function f, represents. This is all taken from our arrow diagram. So with that in mind, let's look at a couple of other arrow diagrams and try to decide if they represent functions. So if I look at example 7.1.2, I want to know, does arrow diagram A represent a function? Well, remember, our definition of a function has two requirements. Every element in the domain must map to an element in the codomain, and every element in the domain that does map to the codomain can only map to one element in the codomain. We have a problem here. Element B in the domain is not mapping to any element in the codomain. So this is not a function, because element B, which is in our domain X, is not mapped to any element in our codomain Y, if I call those X and Y. Well, it doesn't seem like we have that same problem in either case B or case C here. All three of these are mapped, all three of these are mapped. So requirement 1, check for both of those. Requirement 2 says, however, each of our elements in our domain can map to only one element in the codomain. And this is where we have another issue in B. Element C in our domain X here is mapping to two different elements in our codomain Y. So this one is also not a function. And this is because element C in our domain X maps to more than one element in our codomain Y. And that's a problem. Now let's check out our last example here. Again, we have all three elements are being used that are in the domain, and each one maps to only one element in the codomain. So in fact, yes, this is a function, because every element in our domain X maps to only one element in our codomain Y. In fact, they could map all to the same element in the codomain Y, and it would still be a function. In algebra, we call it a constant function. It's just a special kind of function. So it doesn't matter that A and C from the domain are both mapping to 3 in the codomain. All we said is that each element in the domain must map to only one element in the codomain. We didn't say distinct elements in the codomain. In fact, we'll have a rule for that in a different section. Let's look at another example of an arrow diagram and answer some of the same questions that we were asked before, now that we've looked at them a little bit longer. Does this arrow diagram with our function f represent a function? Well, each element of the domain is mapping to an element in the codomain, and each one is mapping to only one element in the codomain. So yes, f is a function because every element in X is mapped to only one element in Y. What would be the domain of our function here? Well, that would be the set of elements in set X, which is the set 1, 3, 5. The codomain then would be our set Y, which is A, B, C, and D, as I said. But the range of our function are the elements of the codomain that are being mapped to, and only the ones that are being mapped to, which in this case would only be the set A and D. Only elements A and D are being mapped to. If we wanted to find f of 1, we simply need to follow the arrow from the input at 1 down to the codomain, which is D. So f of 1 equals D. If we want to know what f of 3 equals, we follow that arrow and we find that f of 3 is A. And f of 5 is D. If we want to start talking inverse images, then if we want to find the inverse image of A is only mapped to by 3. So it's just the set with the element 3 in it. If I want to look at the inverse image of C, then the F inverse of C is going to be the null set because it's not mapped to by any element of the domain. If I want to find the inverse image of D, that's being mapped to by 2 different elements in the domain. And those will be the elements 1 and 5. So if we wanted to, we can represent this function as a set of ordered pairs. And if we did that, our set would look like 1D, in parentheses, comma, the ordered pair 3A, comma, the ordered pair 5D. At the end of section 7.1, we're going to look at theorem 7.1.1, which says if f is a function that maps x to y, and g is a different function that maps x to y, then f equals g if and only if f of x equals g of x for every element in x. So we're going to test that out with 2 different examples. So in example 7.1.4, we're saying let A equal the set 0, 1, 2, and 3. And we're going to define functions f and g from A to A as follows. For every x in set A, f of x equals x plus 3 mod 4, and g of x equals 5 of x plus 7 mod 4. So I've set up a table here that we're going to fill out because we want to know, does f equal g? Well, we know that we're mapping from A to A, so we know our domain is 0, 1, 2, 3. So I went ahead and I filled that in and said x could only be 0, 1, 2, or 3. And you'll notice I have a half for f of x and I have a half for g of x. So for f of x, we have x plus 3 mod 4. So we're going to do this in steps. We're going to write x plus 3 first, and then we will find x plus 3 mod 4. And in much the same way for g of x, we're going to start with 5x plus 7, and then we will find 5x plus 7 mod 4. So let's fill these in. So if x is 0, x plus 3 is 0 plus 3, or 3. If x is 1, x plus 3 is 1 plus 3, which is 4. 2 plus 3 is 5, and 3 plus 3 is 6. Now I need to find 3 mod 4. Well, here's the thing. 3 mod 4, 4 times 0 plus 3 would get us to 3. We can't even get an entire multiple of 4 out of it. So the entire value of 3 is a remainder, so it's our mod. If I do 4 mod 4, well, 4 times 1 equals 4 with no remainder, so my mod is 0. 5 mod 4 is 4 times 1 plus 1, so I have a remainder of 1. And 5 mod 6, 6 mod 4 is going to be 4 times 1 plus 2, so our remainder is 2. If we do the same process for g of x, we have to find 5x plus 7. When x is 0, we get 0 plus 7, which is 7. When x is 1, we get 5 times 1 is 5 plus 7 is 12. 5 times 2 is 10 plus 7 is 17. And 3 times 5 is 15 plus 7 is 22. So then we need to find 7 mod 4, which would be 3 because it's 4 times 1 plus 3. 12 mod 4 would be 0 because 12 is a multiple of 4. 17 mod 4 is going to be 4 times 4 is 16 with 1 as a remainder, so our mod is 1. And 22 mod 4, well, we can't do 4 times 6 because that's 24, but 4 times 5 is 20, so it would have a remainder of 2, so our mod is 2. And in this case, we find that our mods 0 or 3012 and 3012 are exactly the same for f of x and g of x. So we would say since f of x equals g of x for every x in A, f equals g. Every single line has to be exactly the same. It's very much like our logical equivalencies from chapter 2. So let's see if we have the same luck with example 7.1.5, and if that is also a function, or the functions are equal. So in this case, we have a smaller domain. Now we have a domain B of just 0, 1, and 2. I know I have an extra line in the table. I just copied the one from before and pasted it, so that's just an extra row, so you don't need it. You can just pretend it's not there. So we're going to set this one up in much the same way as the last one, because now we have f of x is x squared plus x plus 1 mod 3, and g of x is x plus 2 quantity squared plus mod 3. So we need to start by finding x squared plus x plus 1. Then we'll find x squared plus x plus 1 mod 3 for f of x. For g of x, we'll find x plus 2 quantity squared, and then we'll find x plus 2 quantity squared mod 3. So let's start with x squared plus x plus 1. When x is 0, I get 0 plus 0 plus 1, which is 1. And 1 mod 3 is just going to be 1. When x is 1, I get 1 plus 1 plus 1, which is 3. And 3 mod 3 is 0. It'd be no remainder because 3 is a multiple of 3. If I plug in 2, 2 squared is 4, plus 2 plus 1 is 7. And 7 mod 3 is 1. 6 plus 1. All right, let's try g of x. When x is 0, 0 plus 2 is 2. 2 squared is 4. 4 mod 3 equals 1. When I plug in 1, 1 plus 2 is 3, and 3 squared is 9. 9 mod 3 would be 0, because there would be no remainder, because 3 times 3 is 9. And lastly, 2. 2 plus 2 is 4, and 4 squared is 16. And 16 mod 3 is going to equal 1, because it is 15 plus 1. So we have 1, 0, 1, and 1, 0, 1. So much like the last one, since f of x equals g of x for all x in B, f equals g. And that finishes out section 7.1.